Economic geology is concerned with earth materials that can be used for economic and or industrial purposes. These materials include precious and base metals, non-metallic minerals, construction grade stone, petroleum minerals, coal and water. The term commonly refers to metallic minerals deposits and mineral resources. The techniques employed by other earth science disciplines such as geochemistry, mineralogy, geophysics, petrology and structural geology might all be used to understand, describe and exploit an ore deposit. Economic geology is to know how, why and where minerals are concentrated in specific rocks, structures and tectonic settings within the Earth's crust, and to know how to search for and find these concentrations. In this chapter, we will discuss about economic geology under following sections: history of economic geology, geological concepts and methods of exploitation of mines, economic applications of the several branches of geology and of other sciences, economic geology, application of other sciences. It has been argued that humans have always been scientists. It could also be said they have always been economic geologists. Economic geologists in the sense of prospectors, miners, explorationists and entrepreneurs. One example of this was the mining of copper by Native Americans on the Isle Royale from about 7,500 to 3,000 years before the present. Another example of this making of superglue over 70,000 years ago by people who lived in what is now South Africa. Other commodities mined by early humans included salt, flint. Mining of these dates back at least 100,000 years, silver, gold, cinnabar, lead, melacite and hematite. There was underground mining for flint in France and Britain between 4,000 and 10,000 years ago. Over 7,000 years ago, Egypt sent out expeditions in search of gold, turquoise, silver, tin and lead. The first written record on the formation of ore deposits comes from ancient Greece. Aristotle believed that it was the rays of the sun that caused the concentration of metals. He wrote that when the sun's rays penetrate into the earth's crust and interact with water in various proportions, metal or metallic ores form. In the case of gemstones, Aristotle believed it was starlight whose pure, serene and heavenly rays gave birth to these bright and precious stones. Plato thought there was a great fire at the center of the earth which gave off dense clouds of metal-making vapors. The existence of this great fire was substantiated by the flows and floods of molten rock that flowed over the ground, by clouds of ash, steam and vapor ejected periodically from Mount Etna, Mount Vesuvius and other active volcanoes in the Mediterranean region. The alchemists essentially took Aristotle's and Plato's ideas and modified them. One addition was the idea that not only the sun and the star rays led to mineral concentrations, but so did the rays of other planets and the moon. Thus, different celestial bodies were responsible for different metals. The yellow rays of the sun gave us gold, the planet Mercury quicksilver, iron came from red Mars, silver from the light of the silvery moon, copper from Venus, tin from Jupiter and lead from Saturn. Mineral exploration is the process of finding ores, commercially viable concentrations of minerals, to mine minerals. Mineral exploration is a much more intensive, organized and professional form of mineral prospecting and, though It frequently uses the services of a specialist for prospecting the process of mineral exploration. Mineral concentrations and exploration. A concentration of minerals, what geologists call an ore deposit, is considered economic if it can be mined and sold at a profit. This is a business definition and not a geological one. This definition says nothing about geological processes of concentration and formation. Under this definition, ore is defined as a solid, natural occurring mineral concentration usable as mined or from which one or more valuable constituents may be economically recovered. Thus, includes not only metals but industrial minerals. The search for and finding of ore deposits is technical, and because of all the different earth processes that lead to mineral concentrations, economic geology is an interdisciplinary field. It can involve many different aspects of geology depending on the kind of ore deposit being sought. Geological fields applicable to exploration include volcanology. It is the study of volcanoes, lava, magma, and related geological, geophysical, and geochemical phenomena. Volcanologists frequently visit volcanoes, especially active ones, to observe volcanic eruptions, collect eruptive products including tephra such as ash or pumice, rock and lava samples. Igneous sediment petrology. The study of the composition, characteristics, and origin of sediments and sedimentary rocks. Geochemistry. Geochemistry is the science that uses the tools and principles of chemistry to explain the mechanisms behind major geological systems such as the Earth's crust and its oceans. The realm of geochemistry extends beyond the Earth, encompassing the entire solar system, and has made important contributions to the understanding of a number of processes including mantle convection, the formation of planets, and the origins of granite and basalt. Geophysics. Geophysics is a subject of natural science concerned with the physical processes and physical properties of the Earth and its surrounding space environment. It is the analysis of nature as it pertains to Earth, its environment, and its structure. Geophysicists study a variety of natural phenomena, including the Earth's shape, the dynamics, and its interior and atmospheric processes. Hydrogeology is the area of geology that deals with the distribution and movement of groundwater in the soil and rocks of the Earth's crust, commonly in aquifers. The term geohydrology is often used interchangeably. Some make the minor distinction between a hydrologist or engineer applying them to geology or geohydrology, and a geologist applying them to hydrology or hydrogeology. Geomorphology. Geomorphology is the scientific study of the origin and evolution of topographic and bathymetric features created by physical or chemical processes operating at or near Earth's surface. Geomorphologists seek to understand why landscapes look the way they do, to understand landform history and dynamics, and to predict changes through a combination of field observations, physical experiments, and numerical modeling. Geomorphology is practiced within physical geography, geology, geodesy, engineering geology, archaeology, and geotechnical engineering. This broad base of interests contributes to many research styles and interests within the field. Petroleum geology. It is the branch of economic geology that deals with the occurrence and exploitation of oil and gas fields. Mining geology. It is the branch of economic geology that deals with the applications of geology to mining. Thermal energy is the energy that determines the temperature of matter. The geothermal energy of the Earth's crust originates from the original formation of the planet. that is 20%, and from radioactive decay of materials, which is 80%. The geothermal gradient, which is the difference in temperature between the core of the planet and its surface, derives a continuous conduction of thermal energy in the form of heat from the core of the surface. Economic applications of the several branches of geology and of other sciences. There is no phase of geology which at some time or place does not have its economic application. Some of the phases of geologic science which are most necessary to the practice of economic geology are discussed here briefly. Mineralogy and petrology. Mineralogy is the study of minerals and petrology is the study of rocks, aggregations of minerals. Both are elementary requisites in preparation. There must be familiarity with the principal minerals and rocks and especially with the methods and processes of their identification, with their nature and with their origin. This involves a study of their crystallography, chemical composition, physical qualities, and optical properties as studied with the microscope. Stratigraphy and paleontology are concerned with the sedimentary and life history of the earth. The determination of the ages of the earth's strata and of the conditions of their deposition is required in the practice of economic geology. For example, a detailed knowledge of the succession of rocks and their ages as determined by fossils and other stratigraphic evidence is vital to the interpretation of conditions in an oil or coal field and to the successful exploration and development of its deposits. The success of certain paleontologists and stratigraphic specialists in oil exploration is an evidence of this situation. Certain iron ores, phosphates, salts, potash and other minerals as well as many of the common rocks used for economic purposes are found in sedimentary deposits and require for their successful exploration and development the application of stratigraphic and paleontological knowledge. Structural geology. Structural geology is the study of the physical forms and relations of rocks which result mainly from deformation by earth forces. If rocks remain in their original forms, the structural problems would be a comparatively easy one, but usually they do not. Often they are faulted and folded and mashed to such an extent that it is difficult to go behind the superposed structural features to the original conditions in order to work out the geological history. Not only is a structure study necessary for interpretation of geologic history, but it is often more directly applicable to economic problems, as when, for instance, ore deposits have been formed in the cracks and joints of rocks, and the ore deposits themselves have been faulted and folded. Water resources are often located in the cracks and other openings of rocks and are limited in their distribution and flow because of the complex attitude of deformed rocks. Oil and gas deposits bear a well-defined relation to structural features, the working out of which is almost essential to their discovery. Physiography is a phase of geology which investigates the surface features of the earth. It has to do not only with the description and classification of surface forms, present and past, but with the processes and history of their development. An understanding of the principles and methods of physiography is also vital to an intelligent application of geology to water resources, to soils, to dam and reservoir construction, and to a great variety of engineering undertakings. But as these subjects involve the application of many other phases of geology. Rock alterations or metamorphism. This is one of the newer special phases of geology, which for a long time was regarded as the plaything of the petrographer or student of rocks. With the systematic development of the subject, however, it was found that the extremely numerous and complex alterations of rocks and minerals may be definitely grouped, and that they are controlled by broad principles. It became apparent also that these principles apply both to the economic and non-economic minerals and rocks. Metamorphic geology, therefore, for some geologists, becomes a convenient approach to the subject of economic geology. It has the great advantage that it tends to keep all minerals and all processes of ore deposition in proper perspective with relation to rocks and rock processes in general. Development and valuation of mineral deposits. Developing new or refining appropriate existing mineral deposit grade, tonnage, and spatial models is a necessary building block in assuring mineral deposit resources. The first thrust is approached by three separate but interrelated tasks: develop and implement improved economic filters that sort out which deposit has resources that are economic from those that are not. Design and implement an updated, user-friendly simulation program that is readily transportable. Develop improved or possibly new methods for tract delineations for potential deposits based on modern GIS technology. The second thrust is approached by a single task: investigate and develop practical models and new assessment approaches for important mineral resources that generally occur in sheet form, such as certain industrial mineral deposits and layered platinum metals bearing ultramafic intrusions. Mining and the environment. The environmental impact on mining includes erosion, formation of sinkholes, loss of biodiversity, and contamination of soil, groundwater, surface water by chemicals from mining processes. Some mining methods may have significant environmental and public health effects. Erosion of exposed hillsides, mine dumps, tailing dams, and resultant siltation of drainages, creeks, and rivers can significantly impact the surrounding areas. In areas of wilderness, mining may cause destruction and disturbance of ecosystem and habitats, and in areas of farming it may disturb or destroy productive grazing and croplands. In urbanized environments, mining may produce noise pollution, dust pollution, and visual pollution. Geological disposal of dangerous waste. The production of waste materials during energy recovery processes is an unavoidable consequence of the need for energy. Consequently, safe and efficient disposal or reuse alternatives for these waste materials is essential for sustainable development. For waste streams that must be geological disposed, the largest volumes of energy related waste include coal combustion products, which is also known as CCPs, such as fly ash, coal mining waste, and processed water and drill cuttings from oil and gas exploration, with relatively small amounts of silica resulting from pipe scaling in geothermal energy production. The fate of the vast majority of these energy related wastes is geologic disposal, which ranges from placement in landfills, lined or unlined, or surface impoundments, to deep injection within geologic units. Applications for productive reuse of energy related waste are cost effective alternatives to disposal and are gaining popularity as sustainability of processing becomes more critical. Application of other sciences. Geology is sometimes defined as the application of other sciences to the earth. Considered broadly, there is no phase of science which is not involved in economic geology, and references are made to applications of engineering, mathematics, physics, chemistry, metallurgy, biology, and economics. A comparatively few years ago, alumina, one of the most common and abundant substances of the Earth's crust, was in no general demand except for very limited use as an ornament. Little attention was paid to it by economic geologists as a commercial product. Now, however, aluminium is in great demand, and the raw materials which produce it have become the subjects of intensive study by economic geologists. Geology and engineering construction. Economic applications of geology are by no means confined to mineral resources, including water and soils. In these various relations to the applications of geology are too numerous to classify, much less to describe. While only a few of these activities have in the past required the participation of geologists, the growing size of operations and increasing efficiency in their planning and execution are multiplying the calls for geologic advice. Foundations. The foundations of modern structures such as heavy buildings, especially in untried localities, require much more careful consideration of the substrata than was necessary for lighter structures. In planning such foundations, it is necessary to know the kinds of rock to be excavated, their supporting strength, their structures, the difficulties which are likely to be caused by water, and other geologic features. Surface waters. Construction of great modern dams is preceded by a careful analysis of subsurface conditions. In regard to both the rocks and the water, it is necessary to know the supporting strength of the rocks in relation to the weight of the dam, to know whether the rocks will allow leakage around or beneath the dam, and to know whether there are any zones of weakness in the rocks which will allow shearing of foundations under the weight of the dam in combination with the pressure of the ponded water. Here again, physiographic factors are of vital importance, both in relation to the history of development of the valley and to questions of stream flow and reservoir storage. Tunnels. The digging of tunnels for transportation purposes, for aqueducts, and for sewage disposal requires careful analysis of geologic conditions in regard to both the rocks and the underground water. Knowledge of these conditions is necessary in planning the work, in inviting bids, and in making bids. Disastrous consequences, both physical and financial, have resulted due to lack of consideration of elemental geologic conditions in the past. Slides. Slides of earth and rock materials, both of the creeping and sudden types, have been regarded as acts of providence, but studies of the geologic factors have in many cases disclosed preventable causes. The structural geologist, through his study of folds, falls, and rock flowage, comes to regard rocks essentially as failing structures. Subsidence. Not the least important application of geology to slides in relation to deep mining operations. While the mining geologist has been principally engaged in exploration and development of ores, he is now beginning to be called in to interpret the great earth movements caused by the sinking of the ground over mining openings. For instance, the long wall methods of coal mining have resulted in a slow progressive subsidence of the overlying rock, affecting overlying mineral beds and surface structures over great areas. Railway building. In railway building, the planning and estimation of cuts and fills is now receiving geologic consideration. In order to make sure that no geologic condition has been overlooked which will affect costs, the stability of the road, or the accurate formulation of contracts. Road building in recent years has become a stupendous engineering undertaking which is requiring geologic aid to locate nearby sources of supply for road materials. A considerable number of geologists are now devoting their attention to this work. It relates not only to the hard rock geology, but to the gravel and surface geology. Help of specialists is taken in glacial geology to aid in locating proper supplies of sand and gravel. Geology and engineering courses. Many engineering courses include elementary geologic studies. In recognition of the close relationship between geology and engineering, men so trained, though not geologists, have been responsible for many applications of geology to engineering. With the increasing size and importance of operations calling for more specialization, the professional geologist is now being called in to a larger extent than formerly. A logical trend also is the acquirement of more engineering training on the part of the geologist for the purpose of pursuing these applications of his science. Opportunities for employment are ordinarily found in three main directions: in educational institutions, in the federal and state geological surveys, and in private organizations. The world is the geologist's laboratory. It is the only limit to his activities. The frontiers are near at hand, both physically and intellectually. There are few fields so attractive from the scientific standpoint. There are few in which the successful prosecution of the science can be of so much direct benefit to civilization and can yield such large financial rewards. If, in addition, the opportunities for travel and adventure are taken into account, this profession promises a more interesting and useful life. Thank you.